So we're continuing our look at hybrid orbitals overlapping to make covalent bonds in molecules. This hybridization is a scientific model, or a game, if you will, that we play only when we have to justify the shapes of different molecules. We looked at some examples in the last video. That was completely new. I'm hoping as I go through more examples in this video, it will get easier and easier to anticipate what I'm going to say next. So what I'm going to do is draw a picture of the atomic orbitals overlapping to make this molecule C2H4. To do that, I need to know the shape. Hybridizing is a game we play to explain shape. So I'll need to apply VSEPR theory to a Lewis structure. So go back to the very beginning. I have to make a Lewis structure, and maybe I'll skip that part. Maybe I'll start with a drawing of the correct molecular shape. Now, what I see around each one of those carbon atoms is 3 electron pair domains. So I have 3 electron pair domains. That means I'm going to have trigonal planar geometry around each one of those carbons. So what are the bond angles going to be? For the corners of a triangle, the angle is about 120 degrees. I would say exactly 120 degrees if the 3 things attached to the carbon were the same, but they're different, so I don't want to overspeak the data. We're going to have to use hybrid orbitals. Remember, if I use the unhybridized valence orbitals for carbon, I would use p orbitals that were perpendicular or at 90 degrees to each other. So I'm going to have to play some hybridization game. I can't use sp3 hybrids. sp3s were for 4 electron pair domains, tetrahedral geometry. So let's see if you can anticipate the game I'm going to play. What I began with the last time was looking first at the isolated atom, and then we hybridized or blended the orbitals to get the right geometry. A rule of the game is that the number of hybrid orbitals I want to get out is the same as the number of unhybridized orbitals that I mix. I want to get 3 electron pair domains. I'm going to need 3 equivalent hybrid orbitals, so I'm going to blend 3 of the unhybridized orbitals. I will get 3 new orbitals, and their energies will be the weighted averages of the energies of the orbitals I mixed. Because I mixed 2 of the p orbitals and only 1 s, these new orbitals will have an energy 2/3 of the way up between them. And how do we name this set of orbitals? The naming is based on how I made them. I made them from an s and 2 p's, so I made sp2 orbitals. What I haven't changed is the 2p orbital. It's still there. I haven't changed it at all. Now, this is just a little background. I haven't answered the question. What I'm going to do now is draw that molecule showing the orbitals overlapping. Just a reminder of the molecule we're going to draw. And I think I can make it easier by turning that molecule on its side. Right now, I've drawn it in the plane of the screen. If I turn it on its side, really, those hydrogen in the front would be hiding the hydrogen in the back. I'm just drawing it off a little bit so you can see it. And the reason I'm drawing it from that perspective is it makes it easier to see the orbitals. All right, here I go. Carbon on the left first. Because there's 3 electron pair domains, it's sp2 hybridized. All hybrid orbitals look the same. big fat front lobe, little tiny back lobe. And I'm never going to draw the little tiny back lobe again. It's just too complicated. What's different about the hybrid orbitals? The angle between them. Between the sp3s, we had 109-degree angles because we were trying to explain tetrahedral geometry. Now that we're trying to explain trigonal planar geometry, guess what the angle between the sp2 orbitals is? It's 120 degrees. So I'm going to draw those orbitals in a central plane. Really, the one in the front is hiding the one in the back, but I've shaded the one in the front a little darker and made the dashed line be the one just peeks out behind. You see that orientation of those orbitals at 120 degrees? That should look exactly like this. That's not a coincidence. We're playing this game to explain that shape. So, sp2 orbitals come in sets of 3. There are the 3 sp2s. There is a p orbital left over that we didn't hybridize. Let's put that in. The p orbital is perpendicular to the hybrids. You can take that to the bank. And remember that p orbitals have 2 lobes, one up above and one down below. So just as in every other case, this carbon has 4 valence orbitals. 1, 2, 3 for the sp2s, and the 4th is the p. All right, so there's my sp2 hybridized building block. I am going to show it bonding now to another sp2 hybridized building block. But I'm going to have to reorient it a little bit. To make a covalent bond, to make a sigma bond, I have to have the hybrid orbitals overlapping straight on, end to end. To overlap 2 orbitals straight on, I just made a sigma bond. Now, where am I going to put the other sp2 hybrids? At 120 degrees to those ones. And again, I'm playing that game to make it look like that. So those sp2s are over there. What's left over? The p orbital. So far, I've only seen the first bond of the double bond, the sigma bond. But now I see the p orbitals lined up side by side with each other. And if they could overlap top and bottom, that would make a new kind of bond. Now, it looks kind of funny. The p orbitals I drew in this cartoon aren't fat enough to truly overlap with each other. But if you look at lovely pictures, which I will show you from your textbook in a slide or two, those 2 p orbitals can overlap side by side. When I overlap orbitals side by side, I make a new kind of bond. That's called a pi bond, as opposed to a sigma bond. And that pi bond was formed by the side-to-side overlap of 1 p orbital and another p orbital. So for that double bond, I had 1 sigma bond and 1 pi. Let me jot down a few points about pi bonds to distinguish them from sigma bonds. So where did my pen go? There it is. Pi bonds. They are formed by the side-to-side overlap of atomic orbitals. Side-to-side overlap of atomic orbitals. And that's in contrast with the sigmas, which are formed by the end-on overlap. The electrons that live in the pi bond can live anywhere in this loop. Just like a p orbital has 2 lobes, a pi bonding orbital has 2 lobes. The electrons that live in that orbital can live above the internuclear plane, up in the top half, or below the internuclear plane in the bottom half. So the electron density is above and below the internuclear axis. In other words, between the two nuclei. And again, that's in contrast with the sigma bonds. When I make a sigma bond, the electron density is greatest between the two nuclei where those orbitals overlap. Now, one last thing to finish my picture of this molecule. I haven't put the hydrogens on. I've made the carbon-carbon double bonds, but I haven't made the carbon-hydrogen bond. So let's use the valence orbital from the hydrogen to make the covalent bond to the carbon. We're going to overlap the 1s from the hydrogen and make sigma bonds for each of those. End-on overlap, cylindrically symmetrical, the same all the way around like a cylinder. Now, I am not the world's greatest artist. Let me show you what your textbook shows. So again, for some reason, the textbook chooses to show the orbitals that it's blending from the unhybridized isolated atom on different coordinate systems. I don't know why, but it's combining an s and 2 of the p orbitals. And that makes a set of 3 sp2 hybrids. And there they show the little tiny back lobe that I'm never going to bother to show. What's special about the sp2s? They are arranged at 120 degrees to each other. Coincidence? I think not, because the only reason we're playing this hybridization game is to explain the observed shape of the molecule. So those are the isolated atomic orbitals. Your textbook also shows what I drew with my very crude drawing. This first picture, A, tries to show that the sigma bond formed by the overlap of the sp2 hybrids from the carbons and the pi bond shown like I did with the dashed lines. But I told you that cartoon was very simple. Here's a more realistic picture. Those p orbitals that overlap are really much fatter than I made them look. So they overlap top and bottom and share the electrons between them. So that's really a better picture of what a pi bond looks like. Even better than that, I am going to show you with my model kit what it looks like in 3D as best I can. Now I'm going to show you how I make a double bond in C2H4. We decided that we're going to use sp2 hybrid orbitals, and that was to explain a trigonal planar geometry around each carbon. So this model is showing one of the sp2 hybrids, and I've oriented so that that trigonal plane was in the central plane, and the 2 lobes of the p orbital were up and down. So what I see, as I always see, is 4 valence orbitals. 1, 2, 3 sp2s. sp2s always come in sets of 3. sp2 sets of 3. The p orbital has 2 lobes. That's the 4th valence orbital. So I'm going to let this sp2 hybrid overlap with this sp2 hybridized carbon. And I just made an end-on overlap, which means I made a sigma bond, the first bond of the double bond, between those 2 carbons. Now at this point, I could orient it any way I like, but if I want to make the second bond, the pi bond, I have to orient it so the p orbitals are lined up side by side. And when the p orbitals line up side by side, they can overlap top and bottom and make a pi bond. Oops. Just like a p orbital has two lobes, a pi bonding orbital has two lobes. The electrons that live in the pi bond can be above or below the internuclear axis, unlike a sigma bond where the electron density is greatest in between. So there is my double bond using sp2 hybridized atoms, sigma bond, pi bond. Now you've been very patient with the theory so far. Why are we studying this? A big part of the reason we're studying this is to be able to predict chemical reactivity and understand chemical behavior. So I'm going to show you the difference in behavior between these two molecules, C2H6 versus C2H4, with a very basic look at their orbitals. C2H6. Well, let's see. I'm going to jump straight to the picture using Vesper theory to predict the shape. You would take longer to figure this out, but it would be great if you could pause the video and construct that shape for yourself. Whoops. C2H4, though, is the molecule we just drew. So what do I see here? I see a carbon with 4 electron pair domains. It's sp3 hybridized. This sigma bond is formed by the end-on overlap of an sp3 from one carbon and an sp3 from the other carbon. So in contrast, these carbons were sp2 hybridized, and they had both a sigma bond and a pi bond. The pi bond in C2H4 is going to give it very different properties from the properties of C2H6. First of all, although I draw these molecules as a set static thing, really there's motion at every temperature above absolute zero. And what we can see around sigma bonds in the C2H6 is that there's free rotation around that sigma bond. In contrast, for C2H4, the pi bond prevents rotation. No rotation around the double bond. And I'll show you this with my models as well. But because the pi covalent bond is formed by the p orbitals locked side to side, I can't rotate without breaking a covalent bond. And covalent bonds are strong. That would take way too much energy. That just doesn't happen. More importantly for the reactivity is that we will see again and again next semester that carbon-carbon single bonds and carbon-hydrogen single bonds are so stable they don't react. But the carbon-carbon pi bond does allow C2H4 to be reactive. The electrons in pi bonds are more reactive for two reasons. That the pi bonds are higher in energy than the sigma bonds. Where did my pen go? There we go. pi bonds are higher in energy. And we can tell that's because the pi bonds are formed from p orbitals, which are higher in energy than the hybrid orbitals that form the sigma bonds. Finally, and less importantly, the electrons in the pi bond aren't trapped between the two nuclei like in a sigma bond. The electrons are above and below the internuclear axis where they're more exposed to other reagents coming in. So we haven't studied the reactivity of C2H4, but we can already predict that it will do things that C2H6 won't. Stay tuned for my models. You've been very patient with this very theoretical work. Let me show you how this is going to help us understand chemical reactivity later, and that's what chemistry is all about. What I have here is a model of ethane, C2H6. And just for trivia, I don't care if you know this, this is an example of an alkane. It's a hydrocarbon, has carbon and hydrogen atoms, and only single bonds. That makes it an alkane. What I can also see for each atom is that it has 4 single bonds attached to it. 4 electron pair domains, tetrahedral geometry, which is synonymous with sp3 hybridized. So what I get is this sigma bond between the 2 carbons formed by the overlap of one sp3 from one carbon with another sp3 from the other. That helps me understand the behavior of this molecule. First of all, alkanes with only carbon-carbon sigma bonds will not be reactive. That bond is very stable and strong. The other thing is that this molecule is not static. Because I can get rotation around a sigma bond without breaking it, these molecules are rotating around their single bonds all the time. Remember, sigma bond from the end-on overlap, I can rotate that without breaking the bond. In contrast, the molecule we already talked about with the sp2 hybridization is called ethene, or ethylene as its trivial name. That's just for fun. And just for fun, I'll tell you it belongs to the class of alkenes, which are hydrocarbons that have carbon-carbon double bonds in them, a sigma and a pi. It turns out that alkenes, through their double bonds, are reactive, whereas alkanes weren't. That's because the pi bond is formed from higher energy p orbitals. So it's higher in energy, and therefore the electrons in the pi bond are more reactive than the electrons found in the sigma bonds, which are formed from the lower energy hybrids. The other thing that we'll see is that you don't get free rotation in alkenes. The covalent bond is formed by the side-to-side overlap of p orbitals, and it takes way loads of energy to break a covalent bond. That would only be at a very, very, very high temperature. So under normal situations, there is no rotation around carbon-carbon double bonds, and alkenes will react using the electrons in their pi bonds.